Hello once more, AP Physics 1 students. This video, the purpose of this video is to introduce you to a third kinematics equation, which, as I'll explain in a moment, is not really new. You'll see what I mean by that, but it is a more efficient way it allows a more efficient way to solve some problems. So why don't I just call this, I'll call this when time doesn't matter. And what I mean by that is that there are certain situations where you're not asked to find the time at which something occurs, and you're not provided with information about the time at which something occurs, meaning the time at which some object achieves some final position or achieves some final velocity. Yet you want to be able to kind of predict what the final position or final velocity will be based on some information you're given that doesn't reference time explicitly. So here's a example question here. So suppose a car is moving at let's make it really fast. Let's make it 20 meters per second, and is slowing down at a rate of 5 meters per second squared. All right. How far does the car travel before coming to rest? All right, so we know the initial velocity of the car. We know its acceleration. It's slowing down at a rate of 5 meters per second or 5 meters per second squared. And we want to know from the first moment to the final moment when it comes to rest, how far it travels. Now, we don't need a kinematics equation to solve this. Let me write down the two kinematics equations that we're already familiar with. So kinematics equation 1 looks like this. And kinematics equation 2 looks like this. I'll just indicate here that I'm calling this kinematics equation 1, and I'm calling this kinematics equation 2. So we could solve this problem just using the two kinematics equations that we already have at our disposal. Let's think about how we would do that. Here's my x-axis, graduated in units of meters. Let's have our car start at x equals 0. And our car has an initial velocity in the positive direction of 20 meters per second. And our car has an acceleration which points the other way. Now, I know the acceleration points the other way because it's going to be slowing down. Therefore, the acceleration must point in the opposite direction of the velocity. So according to the value that I gave you in the little problem description, the acceleration is 5 meters per second squared to the left. It's in the negative direction. So the acceleration is going to be a negative value when we plug it into these kinematics equations. All right, and the car will come to rest somewhere here. Eventually, the car will have a final velocity of 0, and we don't know how far the car has moved. We don't know what the displacement of the car is between the first moment and the final moment when it screeches to rest, but that's what we want to find. All right, so in order to figure out how far the car moved, we can't use kinematics equation 1 immediately, because I don't know what time to plug in. If I knew how much time it took for the car to come to rest, then I could plug that time into kinematics equation 1 and find the final x coordinate of the car, and that would be the answer to the question. But I don't know that. Coffee break, sorry. But I can use kinematics equation 2 to first find the time at which the car comes to rest. The car comes to rest at this position here when its final velocity is 0. Its initial velocity is positive 20 meters per second. And I have to add the acceleration times time, but the acceleration is negative 5 meters per second squared, which then gets multiplied by time. And if you solve for time, you get 4 seconds. Eventually, you'll get the feel of this where if the numbers are nice, you won't have to do the algebra even. For example, this car is moving at 20 meters per second, but it's accelerating at 5 meters per second squared the other way. So in this situation, I know it's slowing down at a rate of 5 meters per second. Hence, it will take 4 seconds for the initial velocity of 20 meters per second to be reduced to 0. Okay, once I have that time, this is kind of like the step 1 calculation, I can move on to step 2. Not setup 2, but step 2. And in step 2, now we can use kinematics equation 1. Okay, so kinematics equation 1 looks like this. And the initial position is 0 because I've decided to label x equals 0 to be where the car starts. The final position is going to be, let's see, so 0 plus the initial velocity is 20 meters per second times how much time it travels throughout this whole process, which is 4 seconds, plus 1/2 times the acceleration, which is negative 5 meters per second squared, times the total time of this process, 4 seconds squared. Don't forget to square it. So we have 20 meters per second times 4 seconds. That's 80 meters. And then this next term here is, let's see, 4 seconds squared. 4 squared is 16 times 1/2 is 8 times negative 5 is negative 40 meters. This second term is negative because the acceleration is negative. And so the final position of the car is just positive 40 meters. 80 minus 40 is 40. I guess the car ends up 40 meters to the right of where it started. Now's a good time to point something out. Notice, if the acceleration were 0, then this entire term would be 0, in which case the car would be traveling at a constant 20 meters per second for 4 seconds. This negative term would be 0, and 80 meters would be how far the car traveled. But because it was accelerating in the negative direction and slowing down, it travels less than 80 meters. It only travels 40 meters. Great. So that's our answer. And you know what? In this case, it wasn't too laborious to get this result. We had to use kinematics equation 2 before we used kinematics equation 1. Nevertheless, it wasn't too bad, right? Hopefully you agree this wasn't too bad. So how could we make our lives easier in the future? When we have a situation like this? Would it be possible, for instance, to just have one kinematics equation that we could make use of so that we wouldn't have to go through 2 steps? And the answer is yes, it is possible to do this. So what might this look like? We have our 2 kinematics equations, and in this problem, I only solved for the time. We found it took 4 seconds for the car to stop because I needed to find that in order to plug into kinematics equation 1. But this question really doesn't ask me how much time it takes for the process to occur. It's just something I have to find along the way. Because I don't care about time in a problem like this, I would like an equation that doesn't explicitly reference time. Both kinematics equations 1 and 2 explicitly reference time. So let's eliminate time. I'm not going to run through this algebra. Normally, I would run through this algebra if this were an in-person lesson, but I just don't feel like it. It's the summer. So I'll leave it as an exercise for you. If you want to confirm what I'm about to say, then please do the algebra. It shouldn't take more than 5 to 10 minutes, even if you work slowly. I just don't have it in me today. So solve, this is what you should do. You should solve for t in equation 2. Solve for t in kinematics equation 2. Then plug into equation 1. So you're going to solve for time in kinematics equation 2, then plug the result into equation 1. So now t doesn't appear. Once I have an expression for time that I've obtained using kinematics equation 2, and I plug that expression for time into equation 1, now t no longer appears. The following equation can now be obtained after some algebraic simplification. So solve for time in equation 2, plug that expression for time in for t in equation 1. Now t disappears, and you will get the following resulting equation, which does not reference time. It'll take a little algebraic manipulation on your part, but you should be able to obtain the following. 2 times a times delta x. Okay, what do we make of this? Well, it tells me that the final velocity squared of the object is equal to the initial velocity squared of the object plus 2 times acceleration times displacement. It relates the initial and final velocities not through time, but through the displacement and acceleration that allowed the transition of the initial velocity into the final velocity to occur. And this is a great equation to use for the problem that we just tried to solve before. Consider the following application. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So let's apply this single equation to the problem that we had. The car has a final velocity of 0. The car had an initial velocity of 20 meters per second, which has to be squared in this equation, plus 2 times the acceleration. The acceleration is -5 meters per second squared times delta x. Delta x is what we're trying to solve for. That is how far the car kind of skids before coming to rest. And dropping the units, just for the purpose of the calculation, 20 squared is 400. 2 times -5 is -10. And I think you can see that delta x is just equal to 400 divided by 10, which is positive 40 meters. Once I move this term to the left, it becomes positive. So the result is positive. And that's how far the car moves, 40 meters. So you can decide for yourself, do you like in a situation like this to have a two-step task, step 1 followed by step 2, or would you prefer to use this new kinematics equation, which is just a combination of the previous 2 equations, and using the work that I have in red down here, finish the problem much faster? I think the choice is easy. I'll refer to this as kinematics equation 3 from now on. So this kinematics equation, v final squared equals v initial squared plus 2 times acceleration times displacement, I will call kinematics equation 3. And now you have this at your disposal. If the problem doesn't ask about time, don't play around with the two kinematics equations that reference time. Just use kinematics equation 3. Okay. The one thing I want to add before I wrap up here is that you have to be aware of the fact that delta x, as well as the acceleration, may be negative. Okay, so the acceleration might be negative depending on how you set up your axes and the direction in which the object's acceleration physically points, and also the displacement might be negative, again, depending on how you set up your axes. So I'll give you an example here of where this might be important. Let's see. What if I have an object that is above the ground? Suppose this object is 11.5 meters above the ground, and initially the object is at rest, and then that object falls down and strikes the ground and has some final velocity, and we wish to find that final velocity. I don't care how much time it takes for this object to fall down to the ground. I just know that it falls 11.5 meters down, and I want to know what its final velocity is. All right, so the acceleration of the object, this object is in free fall, is equal to little g. It has a magnitude of little g, which on Earth is 9.8 meters per second squared. So let's find the final velocity here. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times, in this case, delta y. Instead of delta x, I'm going to use delta y because we're dealing with a vertical motion here. That's the y-axis. All right, so let's plug some values in. Well, the initial velocity is 0 because the object is dropped from rest, and that equals 2. The acceleration, I have to be really careful. The acceleration is negative 9.8 meters per second squared. And the displacement, I also have to be careful. The object starts at y equals 11.5 and ends at y equals 0. So the displacement is negative 11.5 meters. The object moved in the negative y direction. All right, the final velocity is therefore the square root of 2 times 9.8 times 11.5, because the negative signs multiply to positive 1. And this is approximately equal to plus or minus, really this should be plus or minus because I put in the square root sign, plus or minus 15 meters per second. Because the object's moving down, I should keep the negative root. I should keep the negative root because the object is moving in the negative y direction at the end of the day. And so the final velocity is 15 meters per second down. Being very formal, writing velocity with the direction as I should. Okay. Hopefully you realize, well, hopefully you saw the previous video and you paid attention and you noticed that 11.5 meters is the height to which that projectile rose in the previous video when you threw it up in the air. And if you'll remember, it was thrown up at 15 meters per second and it will return at 15 meters per second when it gets down to the level from which it was thrown. So these numbers, I chose these numbers because I remember the values. But if for instance, you forgot this negative sign, then you'd be taking the square root of a negative number when you try to find the final velocity, and you'll get an imaginary final velocity. sometimes imaginary numbers mean something really profound is happening. Physicists actually use imaginary numbers all the time. But when you're finding something like a velocity, an imaginary number of meters per second is not something deep or profound. It's just an algebraic mistake. So watch out for that. Okay. Complete the associated homework and good luck to you. We'll be in touch. Bye now.